Okay, welcome everybody. Let's get started with lecture 5 of EfficientML.ai. So today we are going to jump into a new chapter about quantization. So last lecture we learned about pruning to reduce the number of parameters in a neural network. If you think about the total size of a model, of a neural network model, that equal to the number of parameters times the bit width, the number of bits per parameter, right? So you multiply them together, that gives you the total size of the model. So if you want to reduce the size of the model, on one side, we can reduce the number of parameters. That is by using pruning. And the other side will be trying to reduce the precision, the number of bits for each parameter. So that is quantization. We are going to spend 2 lectures about quantization. And here is our agenda. We will first review the numeric type, data types, including the integers, the floating point, the int 8, int 32, int 16, int 4, and int 4. We are also going to learn the concepts of neural network pruning, quantization, followed by 3 types of quantization approach. So we are going to talk about k-means based quantization and linear quantization today. In the next lecture, we are going to cover binary and ternary quantization. So let's start with why do we need quantization? So low bit operators are actually much cheaper. So if you compare the energy of the operation from 8-bit to 32-bit, actually the 8-bit integer operation is much cheaper compared with the 32-bit or the 32-bit integer operation or the 32-bit floating point operation. That's from the operation perspective. From the memory perspective, every data movement is actually, data movement is also quite expensive here. So each memory access equal to hundreds of arithmetic operations. So if you can reduce the size of the model, we can reduce the memory traffic as well. So less number of bit width will result in less energy consumption. So in order to understand how do we quantize neural networks, let's first talk about the data types. How is the numeric data represented in modern computing system? So let's start with integer. Okay, so integer is most common representation, easiest representation. We have unsigned and also signed integer. Okay, so in the unsigned version, each digit represents 2 to the power of 0, to the power of 1, all the way to 2 to the power of 7, if we have 8 bits right here. So this number actually represents 49. But these are unsigned. If you want to add a signed bit, we have 1 bit in the top, so that the remaining bits ranges from 2 to the power of 0, all the way to the power of 6. And here we can find actually we have an overlap. Both all the zeros and 1, 0, 0, 0, they both represent 0. So in order to remove that duplication, a better way to represent a signed integer is by using this 2's complement representation. So what that means is the first bit actually means minus 2 to the power of 7. Okay? And the remaining bits are positive from 2 to the power of 0, 2 to the power of 1, 2 to the power of 6. Only the first bit is 2 to the power of 7. In this case, 0, 0, 0 indicates 0, but 1, 0, 0, 0 no longer indicates 0, but 2 to the power of n minus 1. With that, we can talk about fixed point number. So here we have a decimal point. Okay? So this is a decimal point. Above that, we have the integer bit. Below that, we have the fraction bit. Okay? So from the smallest decimal bit represents 2 to the power of 0, and then 2 to the power of 1, going larger and larger. Since this is 2's complementary representation, the first bit is always negative. And after the decimal bit, it represents 2 to the power of minus 1, minus 2, all the way to minus 4 in this case. Another way to tell which number it represents is still using everything starting from 0. 2 to the power of 0, all the way to 2 to the power of 6. But you shift it by the number of fractional bits, which is 4. Okay, so shift everything by 4. And we can see the represented number is still the same using both interpretations. So that's the fixed point number. Let's get more complicated. To represent a larger range, larger dynamic range, people invented this floating point number. And here we are showing example of 32-bit floating point number in IEEE 754. Okay, so among these 32 bits, we have 1 sign bits in the front, and then 8 bits of exponent, and then 23 bits of fraction. It's also called significant bit or the mantissa bit. And the relationship between these bits is that the definition of this number is -1 to the power of sign bits. Okay, this is the sign bit. And then 1 plus the fraction bit. This is the fraction bit, yellow part, times 2 to the power of exponent minus the bias. Here the bias is 127. And how is that calculated? We have 8 bits of exponent bit. And the bias is calculated by 2 to the power of exponent bit minus 1 minus 1. Okay, so for 8 bits, we have 2 to the power of 7 minus 1, which is 127, which is a constant number, as long as we are using 32-bit floating point representation. Okay, so fraction bit corresponds to the yellow part, exponent bit corresponding to the blue part. Given such definition, we can easily calculate how to represent this number, 0.265625. The representation would be first converted into 1 plus fraction. Okay, 1 plus fraction. So the fraction here is 0.02625. So 1 point something times 2 to the power of minus 2. And here, since the bias is 127, the exponent bit should be 125. Okay? So the exponent bit should be 125 using these 8 bits in blue. And then the 0.0625 is represented by a 1 in the 4th position. Okay? So first converted into 1 plus something to the power of something. Okay? Any questions about this example? So far so good? All right. So let's see, how do we represent 0? Since we have to, if we have to be forced to use 1 plus something to represent a number, then how do we represent 0? Actually, people define this subnormal number. Okay? Previously, we were talking about this representation. Okay? 1 plus fraction to the power of exponent minus the bias. Okay? We call it normal number. The exponent doesn't equal to 0. Here we design a special case where the exponent bits, the blue part, has to be frozen to 0. Okay? In that area, for that area where exponent bits are 0, we define it as subnormal numbers. And the equation is a little different. Rather than 1 plus fraction, here we just use fraction. Okay? And rather than 2 to the power of exponent minus 127, here we have it 2 to the power of 1 minus 127. Okay? So the fraction bit is the only variable here. We no longer have the exponent bit, because here the exponent bit are frozen to be all zeros. So now if the fraction bit is all 0, okay, no matter if the sign bit is 0 or 1, the final result would be 0. Okay? So that's how we represent zeros. And how do we define those subnormal numbers? So let's see, what is the smallest and largest positive subnormal value using the subnormal representation on the right-hand side? So first of all, if it is a normal number, right, the exponent bit cannot be 0. Okay, so in this example, the exponent bit is 1, and then the fraction bit is 0. Okay, so the number would be 1 plus 0, okay, times 2 to the power of 1 minus 127. And the final result is 2 to the power of minus 126. So that's the normal number. For subnormal number, the exponent bit is frozen to be 0. Okay, only the fraction bit is 1 right here. Okay, this is 2 to the power of minus 23. So this is 2 to the power of minus 23 times 2 to the power of minus 126. 126, this is a constant because this is by definition 1 minus 127. Okay, so this is the smallest number we can represent in the subnormal region. So this is constant. This is also constant. So only the fraction bit right here. So actually, you can see this is very similar to the this is a linear representation. Okay, so right here is not linear, like here is linear. What about the largest positive subnormal value? Okay, so on the right hand side, we just fill all the fraction bit to be 1. Okay, in this case, 2 to the power of minus 23 plus 2 to the power of minus 1. So sum it up, we get 1 minus 2 to the power of minus 23. Okay, and then here we have the bias times 2 to the power of minus 126. That is the largest number we can represent in the subnormal region. There are other two cases where if all the exponent bits are all 1, okay, if the sign bit is 0, we use that to represent positive infinity. If the sign bit is 1, we use that to represent negative infinity. Okay? So that is the case for representing the infinity. All the fraction bit has to be 0, and all the sign of the exponent bit has to be 1. What about the sign bit is 1, but the remaining bit is non-zero? We use that to represent not a number. Okay? So actually there is a big waste because no matter what the values are in the fraction bit, they all represent another value, not a number. So actually we're going to revisit this in FP8 representation. So these are the two extreme cases for the mostly coming from the exponent bit. If they're all 0, then that's subnormal number. If they're all 1, they're either infinity or not a number, depending on the fractional bit. So we have talked a lot. Let's put a summary here to summarize what we have learned so far for the floating point representation. First, most importantly, the exponent bit, the blue part, right? If it is 0, or if it is non-zero, or if it is all 1. Okay? If it is non-zero or not the largest number, then that's the normal value. Okay? So the representation would be minus 1 to the power of the sign bit, 1 plus the fraction, times 2 to the power of the exponent minus the bias. That's the simple case. And then we have two corner cases. If the exponent is all 0, then we'll look at the fractional bit. If it is 0, then it represent 0. If they're not 0, then they are subnormal numbers. The subnormal numbers representation differ by 1 plus versus just a fraction right here. Okay? And here the constant is 2 to the power of 1 minus 127. Okay, so that's the exponent equal to 0. And the third case is if the exponent is all 1. Okay? And that either represent positive or negative infinity, or not a number, depending on the fractional bit. And if you see the number representation, from small number to the largest number, we divide it into two regions, the subnormal values versus the normal values. In the subnormal value, the distance between centroid is constant, it's linear quantized, versus in the normal value, the size become larger and larger. So it's good at expressing very large numbers. So people have been keeping improving the efficiency by pushing the precision to lower and lower precision. So from IEEE P32 to P16 to B-float 16. So the exponent width actually represent the range, how much range you can represent. So that is mostly using the exponent. And the fraction width, it indicates the precision. Okay, indicates the precision. So for IP32, we have 8 bits for the exponent and 23 bits for the fractional bits. And altogether we have 31 plus the first sign bit. Altogether we have 32 bits. Well, for the IEEE half precision, which is using 16 bit to represent, we have less number of exponents, only 5 bits for exponent, and 10 bits for the fraction. And later, Google invented this new type, which is BF16, brain float 16. And that is trying to match the exponent bit, number of exponent bits. With the IP32, they are using both 8 bits for the exponent. And we sacrifice the precision. They sacrifice the precision by using fewer number of fraction bits. So we have 8 bits for the exponent, 7 bits for the fraction, plus 1 bit on the top. Altogether, we have 16 bits. So notice the exponent bit for the IP32 and BF16 are the same. Therefore, usually when we are training large-scale neural networks, if IP16 sometimes will diverge, then the good solution usually is to use BF16. Okay, so the question here, what is the following IP16 number in decimal? So let's do a practice. We were given a representation right here. We have 5 bits of exponent, 10 bits of fraction. That's the standard IEEE IP16 precision. So for IP16, what is the bias? So we have 5 bits, 5 minus 1 is 4. Total power of 4 minus 1, that's 15. Okay, so the bias should be 15. So we can use the equation. First of all, the sign bit is minus, right? And then the exponent would be 1, 0, 0, 0, 1 minus the bias right here, which is 17 minus 15, which is 2. And the next will be calculating the fraction bits. The fraction bit is 1, 1 followed by a bunch of zeros. In binary representation, that is 0.75. So this is 0.5, 0.25. Adding them together, we have 0.275. And we use the equation, sign bit 1 plus the fraction bit times total power of exponent bit. Okay, we plug in 0.75, we plug in 2, and altogether we have minus 7 in this case. So this floating point number actually represents minus 7. So let's do a reverse example. We have a decimal number, which is 2.5. How to represent it in brain float 16? I'll give you 1 minute to think about it. First of all, it's brain float 16, right? So it's 1 bit of sign bit, 8 bit of exponent, and 7 bit of fraction. The first thing would be to calculate the bias, right? We have 8 bit of exponent, and the bias equal to total power of exponent minus 1 minus 1. Right? Total power of 7 minus 1, that's 127. Okay, so we have the exponent bias. And remember, we have to represent the number by 1 point something to the power of something. Okay, so 1.25 actually times 2 to the power of 1, that is 2.5. Right? And then we should represent 0.25 and also 1. First of all, the sign bit should be positive. And then the exponent binary right here is 1 plus 127, because the final result should be 1, and then the bias is 127. Therefore, the exponent binary should be 1 plus 127, which is 128. And how do we represent 128? So this is the representation. Next, the fractional bits. Okay, the fraction bits should be 0.25, which is here is 0.5 and here is 0.25. The binary representation is 0, 1, 0, 0, 0, a bunch of zeros. So we can fill in 0, 1, 0, 0 to the fraction bits, and fill in 1, 0, 0, 0 to the exponent bits. And finally, we have the representation in BF16 for the number 2.5. Any questions here? Okay, good. So people want to continue to push the frontier by going to lower and lower precision. So later, NVIDIA has this FP8 using 8-bit floating point to represent a number, starting from the Hopper H100 GPU. Okay, so H100 was super popular in the Silicon Valley these days. H100, H200, usually out of stock. And people are even using these GPUs as collaterals to get financing. And recently, even P4 is coming to the market. The Blackwell B100 is in high demand. So what exactly is happening here? So IP8 can further reduce the precision and increase the throughput. Since we have so few number of bits, we have to be extremely careful how to allocate this number of bits. So first of all, we need a sign bit. So altogether, 8-bit, 1 bit is designated for sign bit, so we are left with only 7 bits. For these 7 bits, we have so many choices. We can do 0 plus 7, 1 plus 6, 2 plus 5, 3 plus 4, 4 plus 3, etc. So actually, these are the two popular used numerical precisions for IP8. 4-bit exponent, 3-bit mantissa, E4 and 3, or E5 and 2. 5 bits for the exponent and 2 bits for the mantissa. So what is the pros and cons for E4 and 3 versus E5 and 2? So remember, the exponent bit is for expressing larger magnitude, okay? Larger dynamic range, versus the mantissa bit is for precision. So if we have 5 bits for exponent, it has a larger dynamic range, a lower precision, versus E4 and 3, we have a smaller dynamic range and a better precision. In this, for this reason, P8, E5 and 2 is really used for representing the gradient in the backward path. Okay, so 1 year later, NVIDIA has this Blackwell. Okay, so Blackwell introduced IP4, 4-bit floating point. It's doubling or even making the throughput even higher. Okay, so with only 4-bit, we have how many choices do we have? We can have these following 4 choices for these 3 bits. We can either have everything as the mantissa, okay, so no exponent bit. That's basically int 4. So we can represent from 0 to 7 for the mantissa part, plus the sign bit. We can represent from -8 all the way to +7. Okay, so that's 16 values to the power of 4, from -8 to +7. And these spaces are equally distanced, so it's linear quantized. To allocate those 4 bits, another way is to do E1 and 2. Okay, we have 1 exponent bit plus 2 mantissa bits. And the number they can represent is actually very similar to int number. So we can have subnormal region where the exponent is 0. So we use this equation to the power of the bias is 0. So this is 0.5. Versus the normal region, 1 plus, so this is 0.75 times 2 to the power of 1 minus 0 is 3.5. So we can represent the numbers from 0, 0.5, minus 1, minus 1.5, all the way to 3.5. Okay, so it's also linearly distanced. So it's pretty much the same as int4, except that they are scaled by 0.5. Okay, so E1, M2 is basically the same as int4, plus it's wasting one slot. We have a positive 0 and a negative 0. Okay? So E1, M2 is the same as int4, except for that it's wasting one slot for 0. It can represent, rather than 16 numbers, it can represent 15 numbers, because 0 is overlapped. 1 plus 2, we can also have 2 plus 1. Okay, so E2 and 1, 2 bits for the exponent and only 1 bit for the mantissa. We can imagine this number will have a larger dynamic range and less precision. So we'll give two examples, 001 versus 111. Okay, so 001, that's in the subnormal region because the exponent bits are all 0. So the equation will be like this. The bias would be 1. The fraction is also 1, so the number represented here is 0.5. For the normal region, the exponent is 3, and the bias is 1. The mantissa is 1, so it's 1 plus 0.5. So this is 1, meaning it's 0.5. So this number is actually 1. Okay? So in that case, we can find the representation for all these values. It's actually from 0, half, 1, 1.5, all the way to 6. And equal to minus 0, minus 1, minus 2, minus 3, minus 12, okay, and scale it like 0 and 5. So indeed, it has a larger dynamic range. It can represent all the way to 12, rather than previously it can only represent all the way to 7. So the extreme case will be using E3 and 0. Okay, all the bits now becomes the exponent bit. So for these values, okay, we have everything as exponent. So this is the very small exponent, 1 minus 7. This is a big exponent, 7 minus 3. Okay. So we can see the representation has the largest dynamic range. It's no longer equal distance, but the distance becomes larger and larger as the value gets larger. The largest value we can represent here is 16 rather than 7. Okay. So that's the E3 and 0. Okay, so far we talked about everything about quantization, about the different numerical representations from int8 to fp32, fp16, bf16, fp8, now fp4 and int4. Any questions so far? Okay, good. If no question, let's move to the next part. What is quantization? Okay, so quantization is the process of constraining the input from a continuous and also large set of values to a discrete set of values. For example, given this signal on the left-hand side, originally the value is continuous. But now we want to convert it to a discrete set. So we divide the region by 5 lines, okay, 1, 2, 3, 4, 5. And we quantize the signal to the closest region. For example, it can only from 0, this is 2, 2, 1, 0, minus 2, 0. Okay, they are quantized to discrete value. Given this example, this is the original image. This is a quantized image in 16 colors. You can see the color map becomes discrete. And the difference between the input value and its quantized value is referred to as the quantization error. And our goal is try to minimize this quantization error. So this is the agenda for the lecture. So initially we start with something that is a floating point, using floating point arithmetic to do the computation and using floating point to represent the weights. Then we first going to introduce k-means based quantization. So we have a code book. We have a code book, it can be anything, and only store the index within that code book. So the storage is including 2 parts, the integer weights, it's no longer floating point, it's integer, together with the floating point of code book. And the computation will be done using floating point arithmetic in this case. So what is good and bad? So the good thing about it is that we are saving the storage by using integer weights. And the limitation is that we are not saving the computation. we're still requiring to use the floating point arithmetic since we have to decode the weights. So let's jump in deeper into how do we deal with this k-means quantization. This is an example matrix, a 4 by 4 weight matrix represented using 32-bit floating point. So we don't need the numbers to be so accurate. You have 2.09, 2.12, 1.92, 1.87. We don't care such high precision. We can just approximate everything to 2. Okay? So that's the design philosophy. So what we do here is we do the k-means clustering to assign a color to each value. For example, everything that is close to 2, we assign the blue color, like 2.09, 2.12, 1.92, 1.87. Okay? And similarly, we do that for other colors. Everything that's closer to, that is very close to -1, we color them in green. Okay? We color them in green, like 0.98, 1.08, 1.13, 0.91. We all quantize them to -1 by clustering. So what we store here is the index into the centroid. Okay, so this is centroid 0, centroid 1, 2, 3. So for this 2.09, since it's closest to the blue centroid, and that blue centroid has index of 3. So here we only need to store the index 3 on the top. So previously we are storing a 32-bit floating point 2.09. Now we only store a 2-bit integer index that is going to index into this codebook. Similarly, we can do it for the rest of the weights. Let's do one more example. We have 1.48, 1.53, 1.49. They're all very close to 1.5. Where is 1.5? That's the second centroid. What is the index? That is 2. So instead of storing 1.48, we store the index 2. Okay, one level of indirection. So how do we reconstruct the weight matrix using the codebook? So on the right-hand side, it's showing the reconstructed weights. Okay, so for example, here we have index 1 and 1. We look into the table. 1 actually indicates 0, so we put 0 in the corresponding location. So we can now calculate the quantization error, which is subtracting between this original weight versus this reconstructed weight, and we can get this quantization error. What about the storage? So originally, each bit, each weight is represented using 32-bit floating point. And how many values are there? We have 4 by 4, that's 16 values. So altogether, that's 512 bits, or 64 bytes, since each byte equal to 8 bits. What about after? So we have two portions. One is index, one is the centroids. So for the index, how many bits do we have for each index? 4 values, so 2 bits are enough to represent the index. How many indexes are there? We have 16 indexes. So altogether, 2 times 16, we need only 32 bits. Okay, how many bytes are there? Only 4 bytes. Okay, it's a lot smaller compared with the original storage. But don't forget, we also need to store the codebook. So the codebook is floating point, high precision. Okay, so each entry in the codebook is represented using 32-bit. We have 4 entries. Okay, so times 4, that's 128 bits, or 16 bytes. If we sum them up, 4 bytes plus 16 bytes, altogether we need 20 bytes to using this k-means cluster quantization, which is about 3.2 times smaller compared with the original size. So this is the this is just an example case. In the common scenario, assuming we have n-bit quantization and the number of parameters equal to m, which is much larger than 2 to the power of n, which is usually called the case where we have a very big matrix, much larger than 16 by 4 by 4, but the code book is the same. In that case, originally each weight is represented using 32-bit, and we have m weights, we have 32 m bits. And after that, we have n bits. Nowadays, we have n bits, in this case 2 bits. 2 bits times m, so that's n bits, plus the code book. Each entry is using 32-bit. We have 2 to the power of n. Here is 2 to the power of 2, which is 4 entries in the code book. So that's 2 to the power of n plus 5 bits. And since m is much larger than 2 to the power of n, we can ignore the second term. So the compression ratio would be 32 divided by n times smaller. If n equal to 2, in this case, if this matrix is super large, then the saving would be 32 divided by 2, that's 16 times. If we have 4 bits, which we are going to implement that in the homework, we have 4 bits, we have 16 entries in the code book, then what's the compression ratio? That's 32 divided by 4, that's 8-bit compression, smaller. Okay, so this is the representation. How do we fine-tune the model that is quantized using k-means quantization? Okay, we will get a gradient matrix. So after backpropagation, we get a gradient matrix. So we are going to color them using the same color as the weight. Okay, so blue, green, red, blue, green, red, using the same color. And then we're going to do a group by operation to group the same color together at 0 point. So these 4 blue values are grouped together, okay, and these red values are grouped together. So they correspond to the same centroid. We are going to reduce them by summing them up, okay, and then multiplied by the learning rate, subtracted from the original centroid, then we get the fine-tuned centroid. So that's one iteration of the SGD on a k-means quantized neural network. So we first do a group by operation, and then do a reduction by summing them up, multiplied by the learning rate and subtracted from the original centroid. That will give you the updated centroid. How does that work with respect to the accuracy? So this is showing the quantization only. What is model size ratio after compression? So we can go much smaller, and this is accuracy degradation until about 10%, 11%. We have very low accuracy degradation, and after that, the accuracy is going to drop very quickly. How does it compare with pruning only? So this line is showing the pruning only result in purple, and we can find that they are pretty much closer, roughly around 10%. The accuracy begins to drop. But the good thing is that pruning and quantization can be combined together. Okay? We can do both pruning and then quantization. That gives you the highest compression ratio. Okay? Just a few percent, the accuracy is still very well maintained, which is a good thing. So practically, should we do pruning first or should we do quantization first? What does the model size ratio mean for quantization? So if the original model size is 100 megabytes, now it's 10 megabytes, then the ratio will be 10%. Yeah. If originally you are using 32-bit and the model is 100 megabytes, now you are using 8-bit, the model size would be 25 megabytes, and the ratio will be 25%.
For k-means quantization, why do you add up the gradients and not like take a mean of the gradients?
So there are actually, that depends on the number. The reduction can be done by, let me see, actually, right here we are calculating the mean. Let me see, let me double check. This is just doing the sum, I believe. Yes, this is just doing the sum. Because they are all updating to the same centroid. A lot of people want to nudge the same centroid. Therefore, we sum them up. Somehow they can be partially cancelled by multiplying with the learning rate, but really matters is how many numbers will go to the same bucket. The more number of want to go into the same bucket, the more we want to nudge the weight. So therefore we are doing the sum right here. You're very welcome to try trying to do the mean, the average. That's the beauty of deep learning. It's not a fixed science or it's engineering. So basically use the method that works the best. Not necessarily this is the best approach. Yeah, that's just what I did in the paper 8 years ago. So back to our question, should we do pruning first or should we do quantization first?
I feel like you should do pruning first because then your centroid will be more like accurate afterwards, right?
Right, that's a good point. Since you want to do quantization, pruning first because you want to first eliminate a lot of redundant weights. Okay, so you have fewer number of weights to quantize, reducing your workload to quantize and potentially reducing the quantization error. So first, get rid of those redundant weights before you quantize. So this is the weight distribution. After fine-tuning a pruned model, why there is a big bump here? Because everything close to zero are pruned using our magnitude-based pruning approach. Okay, everything close to zero, they are set to zero. So these areas get flatter because after fine-tuning they become flatter. Okay, so what does it look like after quantization? The values becomes discrete. So rather than continuous distribution, they become discrete. So only a couple of centroid. This is centroid, this is one, this is another one, this is another one, this is another centroid. Okay, the value becomes discrete. Question?
I'm wondering if you encountered any situations where quantization might be preferred to pruning?
Can you repeat the question?
Would there be any situations in which quantization might be preferred to pruning?
Any situation where quantization would be more preferable than pruning. Depending on the pruning granularity, for coarse-grained pruning, any hardware can accelerate it, so it's best to combine them both. I don't see any scenario where you don't want to combine coarse-grained pruning with quantization, unless your hardware doesn't have any low precision unit. You can only do pruning. But I don't see a reason where you cannot do pruning, but only do quantization. At least you can do coarse-grained structured pruning. So the remaining weights are still dense. Okay, so after the fine-tuning, we can see a slight difference right here between these two slides. You can see the centroid shifted a little bit. From here to here, the centroid shifted a little bit. That is due to when we are updating the weights. Remember right here, just now I have a question. We are calculating the gradient, sum them up. Since all these blue gradients are trying to update the blue centroid, we want to sum them up. Apply the nudge, apply the change all together to change this centroid. And the centroid will get changed after a couple of iterations. And we indeed observed that change between these two slides. This is before, this is after. This is before, this is after. You can see the slight change about the position of the centroid. And another question is, is the assignment able to get changed? And that is so true. If the nudge is so big, one value might also become another bucket. So the assignment, the color assignment might also change. We are going to implement that in lab 2, which we are going to release next week. Actually, we already released it, so feel free to try it out to implement this k-means quantization by yourself. And finally, how many bits do we need in practice? Previously, we are showing 2 bits for illustration purpose. In practice, we find for, this is for AlexNet convolution layer, after 4 bits, the accuracy is going to drop very sharply. But before that, the accuracy can be very well maintained. For the FC layers, after 2 bits, before 2 bits, the accuracy is still well maintained for the top 5 and top 1 accuracy. And in practice nowadays for large language models, we are going to see that in lab 4, 4 bits is very enough. It's quite good maintaining the accuracy of large language models, these transformer models. So another idea proposing this deep compression paper is using Huffman coding to further compress it, since the weight distribution is not uniform. Okay, so some of the weights appear very frequently, some of the weights doesn't appear very frequently. So we can encode the weights using different number of bits. For different weights, they can use different variable length encoding. So we can use fewer bits for the more frequently appearing one, and use more number of bits for those less frequently appearing weights. So put them together, we have this 3-stage pipeline for deep compression. First using pruning to reduce the number of weights by tune the model, prune it, retrain it, repeat it. And then by quantization, we first cluster the weights using k-means clustering, generate a code book, 16 entries, 4 bits, or 4 entries, 2 bits. Then we quantize the weights with the code book, retrain the code book, and repeat this process. And finally, we can encode the weights using different bits for different weights. And as a result, we can achieve very high compression ratio across different neural nets. 40 times for the net, 39 times for the net 5, 35 times AlexNet, even the Google Net, ResNet is compressed by an order of magnitude. And this is the model size before and after the quantization. And this is original accuracy and the compressed accuracy. The accuracy can be very well maintained. Even for very small and compact neural nets like SqueezeNet, we are going to introduce in the neural architecture search session. It's very small to begin with, like 0.47 megabytes. Okay? Begin with, it's 4.8 megabytes to begin with. Compared with AlexNet, it's already 50 times smaller. Okay? 50 times smaller compared with AlexNet, with exactly the same accuracy. But even that can be compressed by deep compression by an order of magnitude. So 10 times smaller, maintaining the accuracy while the model is only 0.47 megabytes and put it in your pocket. Okay? Question?
For the k-means component, is k just a hyperparameter?
Yes, that's the hyperparameter. And how to find that hyperparameter? We're going to find where the accuracy begins to drop. Here, the accuracy drops at 4 bits, so k equals to 16. Here, accuracy drops at 2 bits, so k equals to 4. We're going to play with that in the homework. Good question. All right, so how do we compute on a k-mean space with quantization? We have to decompress it, okay, by mapping it from the index into the original weight. So here we have the code book, we have the quantized weight, we have to first decode it from unsigned int, which is just the index, into the floating point weight. Okay, and all the remaining operations will be done in floating point. So it saves the storage, but it doesn't save the computation. But it's still very helpful for in the modern transformers and large language models, because for single user, for on the generation phase, it's completely memory bounded, not compute bounded. So using IP16 is totally fine, but reducing the memory footprint by 4 times compared with IP16 is super helpful. Okay, let's take a short break before we jump into the next part, which is linear quantization. All right, welcome back. So let's continue the discussion about linear quantization. So now we want to use integer weights to represent the values, and also we want to use the integer arithmetic to do the computation, so that we want to get acceleration and also get a storage saving. So let's see what is linear quantization. This is very widely used if you're using a mobile phone running an application locally. That's highly possible. Linear quantization is used here. So what is linear quantization? So given this is our familiar matrix, 4x4 weight matrix. So now we want to quantize them into only integer values. Okay? Right here is 1, 0 is minus 2, 1, 1 minus 1, 0, 0, 0, and 0, 1 equal to 1. Okay? So now this is the quantized version of the original matrix. So 2.09 becomes 1, minus 0.98 becomes minus 2. So here we have two parameters. We are going to learn how to determine these parameters, but let's just see how that works. We have to define 0 point and a scalar, okay, and a scale factor. So we subtract the matrix with the 0 point, multiply the scaling factor, and we get the reconstructed weight matrix. So 2.09 becomes 2.14, minus 0.98 now becomes minus 1.07. Okay, and this is the quantization error. It's quite small, so they are roughly very well correlates between and after quantization. So the magic here is how do we calculate this 0 point, 2-bit size integer, versus the scale, which is a 32-bit floating point number. So what is a 0 point and scaling factor? So we are going to map this integer value q, subtracted from the integer 0 point, and multiply by the scaling factor, we get the floating point value. Okay? So basically z, which is the 0 point, is allow a real number r equal to 0, which r equal to 0, to be exactly represented by a quantized integer z. So z will be mapped to 0. Okay? And then we have another scaling factor to scale the dynamic range. What that means is that we have a floating point dynamic range from r min to r max. This is the range of the weight values. We also have a dynamic range for the integer value from q min to q max. And the 0 point maps z to 0 from integer space to floating point stage, to floating point range. So this is corresponding to different number of bits. You have 2 bits, the q min equals minus 2, q max equals to 1. You have 3 bits from minus 4 to positive 3. So the integer q min and q max are fixed. So how do we calculate the scaling factor? Okay, so q min has to be mapped to r min, and q max has to be mapped to r max using the equation where we map q max minus z scaled by s, we get r max. Q min minus z scaled by s, we get r min. We can subtract them and then divide it. We can get the scaling factor equal to r max minus r min, which is here, r max minus r min, the dynamic range of the floating point range, divided by the q max minus q min, the dynamic range of the integer scale. Okay? So s can be calculated in this way. R max minus r min divided by q max minus q min. So given our matrix, this is our familiar matrix. The max value is 2.12, mean value is minus 1.08. We use this equation to calculate the dynamic range of the floating point versus dynamic range of the integer, and now we can get the scaling factor to be 1.07. That's how we calculate the scaling factor. Now we can calculate the z. Okay, so since we already have s, we can plug in s to get the z. And it has to be an integer, therefore we have to round it to the closest integer value. In our example, q min is minus 1.08 in the right part. We plug in the equation, and then we can plug in the q min, which is minus 2, since we have only 2 bits. Q min is minus 2. R min is minus 108, minus 108. S we already calculated is 1.07. And we rounded the z. 0 point is minus 1. So now let's talk about linear quantized matrix multiplication. So how do we use integer unit? Only use integer unit to calculate the matrix multiplication. So linear quantization is a affine mapping from integers to real numbers using the equation we just talked about. So consider the following matrix multiplication: y equal to wx. Originally, there are floating point values. Now we want to convert it into integer values. We are going to implement it in the lab, so I will pay really attention to the derivation for the remaining 20 minutes. So we plug in the equation where r equals to s times q minus z. So s times q minus z for the output, for the weight, for the input activation. Plug them in, and then we rearrange them by moving sy to the right-hand side, move zy to the right-hand side, and then we can expand the equation from this row to this row, from all the way we get these 4 different terms. So far, very simple derivation. So we want to use n-bit, for example, 8-bit integer multiplication, and use 32-bit integer addition to prevent overflow. So first of all, the scaling factor, and then we have this n-bit integer addition, and then this yellow part are all constant. The weight is constant. The 0 point is a constant. It's profiled. 0 point is constant. So all these can be pre-computed. It's not in the runtime. No runtime overhead. And now let's focus on the scaling factor. So empirically, the scaling factor SW as x divided by sy is between 0 and 1. And from this paper right here, it can be represented by 2 to the power of minus n times a value, okay, a fixed point value between 0.5 and 1. And this multiplication can be done with a fixed point multiplication. And the 2 to the power of minus n can be done by simple bit shift. So we don't need floating point unit to implement this blue part. So for this part, we scale them to n-bit integer. This part can be pre-computed, and the last part is n-bit integer addition. And let's look at the middle part, the ZW times the QX. So the 0 point of the weight. What is the distribution like? So it's roughly following a normal distribution. Okay? So roughly centered around 0. Okay? So we can safely set ZW to be 0 because it's very symmetric, and roughly 0 is mapped to 0. Okay? So we set ZW to be 0. And what I mean is that originally Z maps to 0, now 0 maps to 0 from the fixed point to the floating point range. In that case, we can simplify the equation where now Z becomes 0, so the scaling factor will be using the absolute value of the R divided by 2 to the power of n minus 1. Okay, much simpler calculation for the scaling factor. Previously, we have to do this calculation to map it. Now we just do a much simpler calculation to map it. So we can safely get rid of this green part since ZW is 0, it's symmetric. Okay, then we are left only with these 2 terms. The first term, which is can be done by 8-bit integer multiplication with QX and QW. That's where the most of the weight lifting is happening in the computation. And we can, since ZW is 0, we are only left with a single term. These are constants because Z is a constant, and QW to quantize the weight is also constant, and we are only left with the ZY. And the blue part is the bulk of the computation, where the bulk of the computation happens. Now let's consider adding back the bias. Okay, so far we are ignoring the bias. Now we consider following the fully connected layer with the bias. Okay, so the bias can be also, we plug in the equation right here. The bias can be also represented by subtracting the bias and then multiply with the scaling factor of that bias. Since previously we mentioned ZW is 0, it's following a normal distribution, we can set ZW to be 0. So integer 0 maps to the floating point 0. We can eliminate everything associated with the ZW, so we are left with the equation here. We can force this SB, okay, let's see it again. the scaling factor for the bias versus the scaling factor of the weight and activation versus the ZB. Similar to the weight, the distribution of the bias is also following a normal distribution. We can set ZB to be 0. Okay, so we can set ZB to be 0, and we force SB to be equal to SW times SX, so that the equation can be simplified in this way. We absorb QB together with these two terms. Okay, so we force SB equal to SW times SX. So let's continue the derivation. We are going to move SY to the right hand side and move ZY to the right hand side, so we are left with this equation. So QB, ZX, QW, quantized weight, 0 point of activation, bias of the bias, they're all constant, so we can pre-compute them. And we define the QB minus ZX QW to be Q bias, since it's a constant. Then we can simplify all the equation to something like this. Let's look closer into this equation. The blue part is the bulk of the computation. Most of the weightlifting is happening in the blue part. That's a low bit integer multiplication. And we can rescale the scaling factor to n-bit integer, like 8-bit integer followed by shift. We just discussed about it. And finally, we have n-bit integer add. Okay, so now everything can be cast into low precision integer operation. What if we use convolution rather than a fully connected layer? So compared with the fully connected layer, now we run the convolution. Essentially, derivation is pretty much the same. You're going to visit in the lab. We just replace multiplication with convolution. They're all linear. Okay, so blue part is where this green part is where most of the computation is happening. So this is the computation diagram where we have previously the quantized weight. This is the quantized input activation. We do the integer conv. The convolution was added with the bias. The sum is summed using a 32-bit register for the summation to prevent overflow. Okay, so 8-bit int, 8-bit int, 32-bit int for the summation register, and all the sum is done in 32-bit. Okay, and the bias scale by the scaling factor, and then add the 0 point, and finally we get the quantized output. So what's the difference with the k-means quantization? Previously we are using 32-bit floating point to do all the computation. Now we are using integer to do all the computation. So we are saving not only the storage, but also we are saving the compute. So we are going to implement this in lab 2, so make sure you understand the lecture here. I'll pause a little bit for you to, in case you have any questions for the derivation.
If we're shifting the range, how does this work with like ReLU layers?
Yeah, for ReLU we basically have nothing on the left, so we are wasting half of the dynamic range. If you set the bias, the 0 point of the bias to be 0, which is this case, you waste half of the dynamic range. Okay, if no more questions, let's see how does the accuracy compare with the floating point. So this figure is showing the floating point versus 8-bit integer. Okay, so this is the latency versus the accuracy. Ideally, we want something at the top left corner, and consistently the 8-bit is having a better trade-off on the plot compared with the floating point counterpart. Higher accuracy, same latency, or same accuracy, lower latency. On the left-hand side, it's showing for greater than 50, exception V3, the floating point versus integer accuracy. And nowadays, this 8-bit quantization becomes very mature. That's the solution to accelerate and compress neural nets. And most of the hardware have 8-bit integer unit, so that's very widely used. If you're using running neural nets on the phone, on a microcontroller, on an edge device, this is a very critical solution. All right, so that concludes our second part, which is the linear quantization. So different from k-means quantization, which only saves storage but doesn't save computation, linear quantization can save both storage and the quantization. So what is next? Can we go even lower precision? So we are going to talk about binary ternary quantization in the next lecture. Only use 1 bit or 2 bits to represent each weight. Okay, so let's summarize today's lecture. We first introduced the data types, floating point, what is integer, what is the floating point representation, what is the exponent bit, what is the Marquesa bit, what is subnormal region, how do we represent very big numbers, what is FP4, FP8, different configurations, E2, M4, etc. E5, M2, etc. And also we visited the basic concept of neural network quantization to convert the weight and activations to discrete values. And then we introduced 2 types of quantization. One is k-means quantization, we're going to see them in the homework, and also the linear quantization. We went through a long derivation, make sure we can translate them into the code in Lab 2. And here are some references, and that's all for today's lecture. Thank you.